Today, half of humanity, around 3.5 billion people, live in cities. Although urbanization generates important benefits for people, such as the creation of employment opportunities, cultural spaces, quality educational facilities, and health infrastructure, as well as an overall improved standard of living, urbanization is also rapidly leading energy consumption, pollution, and congestion to alarming levels. For example, much of the urban population of the world currently depend on a car or other motorized vehicles for their mobility, which accounts for an appalling 1 billion cars worldwide. This not only makes cities important sources of air pollution, but are also the places where annually more than 500,000 road traffic fatalities take place. The problem is that all of these numbers are only increasing. It is forecasted that by 2050, more than 6 billion people, about 70% of the global population, will live in urban areas. Therefore, an international push towards sustainability is crucial not only to lessen the strain on social, economic, and environmental well-being, but also to fast-track national and global development. In the 2012 United Nations World Conference, global leaders unanimously recognized that transport and mobility are central to achieving the sustainability targets of the world. However, notwithstanding that this generation has witnessed the haste in which technological changes have occurred, in terms of mobility, we are still chained to the past through the paradigms that the car industry has established for the past 100 years.
For decades, we have been focused on the incredible benefits of using solar energy to sustain humanity's future. So using solar energy has been the core principle of our academic programs, which have been welcomed with strong interest and commitments by our students. In 2012, the first Spartan Superway work team came to life with the collaboration of many enthusiastic students and professors. And now universities around the world are starting to embrace the solar alternative we are developing to replace our current fossil fuel dependent transportation paradigm.
In this video, we will explain the overall process we have followed to find new answers for mobility challenges around the world. The first step that our teams have followed to face the immense task of developing a new transportation paradigm was to perform a thorough intellection phase to unravel the intricate mesh of factors that conform an urban transportation system.
Any innovation project of this magnitude requires a deep understanding and intellection phase that must provide key information and insights to guide the decision-making through the project.
From the very beginning, we knew that a project as complex as this one would require different teams addressing different problems at the same time. That is why we have recruited students and experts from different professions and from all over the world.
It's important to understand that if any university wants to take on a project of this complexity and scope, it's vitally important to develop collaborations with many disciplines, either within or outside the university.
This is the reason why we have divided our team into 4 main subdivisions that within them have divisions of their own, which are engineering, urban planning, architecture, and industrial design. We soon realized that for our proposal to be useful for people, it was of the utmost importance that our design became flexible enough so that it could be adapted to any context, urbanized or not. Therefore, our teams have used information coming from contrasting contexts, from cities with overwhelming traffic problems to places where there is no mobility infrastructure at all. With a clear understanding of these general goals, each team set goals and procedures of their own. But more importantly, because of the knowledge and techniques to solve problems from one field constantly overlap with those of another, the need of dynamic communication and cooperation between the teams had to be encouraged and enabled. The main directives that remained relevant to each and every team were efficiency, cost effectiveness, user safety, and user acceptance. Our teams have also studied the sustainability goals of international organizations such as the ones put forward by the United Nations and the World Health Organization.
Only a precise balance among all of the factors will provide any project with a solid opportunity of becoming a functioning product in the outside world.
Based upon the analysis of all the data we had obtained, we set out the goal to design a new transportation system, and we called it Spartan, Solar-Powered Automated Rapid Transit Ascendant Network.
Spartan Superway is a transportation system that can be built economically and rapidly, and it's adaptable to both urban and suburban densities. It can be readily expanded, which helps to reduce gridlock traffic by moving people and goods on an elevated guideway with photovoltaic, solar energy, and self-driving zero-emission vehicles.
Since our base of operations has always been located at the San Jose State University, which, as any other university in the world, has its own very particular mobility problems, we began to study such problems to elaborate an initial hypothesis. If we could connect San Jose State University's different campuses located blocks away from each other, without altering the current urban infrastructure, we could begin to demonstrate the flexibility and adaptability attributes of our system. It also became clear that San Jose was the ideal testing ground to install our system, as it is located in the very heart of the innovation capital of the world, Silicon Valley. If we succeed, San Jose State University would become the first university in the world to own its own experimental, fully automated photovoltaic transportation system that would not only communicate its different campuses, but would also put it at the front of international transportation innovation. Additionally, our team of urban planning did an extensive site reconnaissance to determine the optimal location of the route and its stations so that they could provide a truly useful service to the community. The objective then would be to connect two campuses located several blocks from each other, one being the main campus, and the other the sports campus with its stadium. One scenario within this context that we found interesting to study even further was the one of game days at the stadium, when the amount of people that move from one campus to the other increases considerably, causing congestion, accidents, noise pollution, among other things, which our system could substantially reduce. While the urban planning and user experience teams were working on defining the context and specific needs that had to be contemplated, the rest of the teams were working on designing the different elements that conform the system. The conjoined work between the teams of engineering and industrial design has developed what we call the pod. The pod is a self-driving, fully automated vehicle powered by photovoltaic energy that runs suspended from a bogie that runs on a guideway. This configuration provides a fast, highly efficient, and very safe form of travel. Our team of engineers has developed a bogie that works under the premise of safety redundancy. If one half of the bogie should malfunction, there is an independent second half that can move the bogie and its passengers to safety.
The bogey's design is based on more than 8 years of development by Spartan Superway, with valuable technical contributions from engineering students at San Jose State University, Swenson Solar, the International Institute of Sustainable Transportation, industry mentors, and support from our sponsors.
One key feature of our design is the specially designed mechanism called switching arm, a device that allows the pod to change its trajectory. This switching arm is built on the bogie instead of being part of the guideway, as it is normally the case in railway systems. The switching arm mechanism is the key feature that allows the guideways to be more simple in their configuration and construction compared to traditional railways. This allows the system to become more than a simple closed loop with just a couple of stations. Instead, it will have the possibility of growing into a network very similar to the current grid of streets in cities, and with as many stations as necessary.
We are designing the interior of this pod to be adaptable to different travel circumstances. In terms of passenger transportation, the interior has been thought out to be completely rearrangeable depending on the different user needs we might encounter.
Within the pod, users will find a number of possible sitting configurations that will allow people with different needs to find a way to travel safely and comfortably. It is important to remark the safety measures that have been devised to maximize safety throughout the ride. For example, the opening of the doors create a temporary corridor that protects users from gusts of wind and safely conducts them in or out the vehicle. One of the lessons that must be learned from the 2020 pandemic is that public transportation must be able to react to such events and provide alternatives where contagion is diminished. That is why the cabin design contemplates dividing the pod into smaller compartments to keep people isolated as much as possible, something that today is almost impossible to do in most public transports. The Guideway. The Guideway's design is the result of all of our teams working collectively. The engineering and architecture departments have faced the challenge to make the Guideway and the columns that support it as modular as possible so that prefabricated parts can be brought from factories to be assembled on site. The flexibility and versatility of our column and Guideway design should allow us to place the system wherever it is necessary without affecting any of the currently installed urban infrastructure. Even more, one of the main obstacles we had to overcome was to find a way of crossing San Jose's freeway's overpasses. After studying different scenarios, the decision was made to go underneath the freeway through the underpasses, as our models and simulations showed that it was possible to do so, thus connecting parts of the city that frequently remain inaccessible to people without a car. The combined function of the switching mechanism on the bogie and the careful placement of forks on the guideways will allow the pods that need to stop at a station to divert from the main guideway without interfering with the rest of the transit. All of these designs and functional features would make little sense, especially today looking into the future, if they were not powered by a renewable energy source. Therefore, the whole system will be covered with solar panels that will provide power not only to the pod cars, but also to the stations and will provide electricity to all of the system's requirements. The use of photovoltaic energy to power the system has been a crucial aspect of our concept since its very inception. Therefore, Our team of engineers has conducted a series of simulations under different circumstances to find the energy requirements of the system. They are also trying different configurations to find the optimal arrangement of electrical components to use solar energy's full potential. Finally, the work of our architecture, urban planning, and industrial design teams came together to design our stations. The stations. Elevated access platforms that allow riders to board the pods in the most safe and efficient way. The North Station. Our northmost station has been thought out to be located within the main campus of San Jose State University. While scouting the area for some open spaces where to locate this station, we came across a small plaza or corridor between two buildings that, because of its location and dimensions, became the perfect spot for our purposes. This design is a good example of a station that can only exist on one side of the road, on a two-way street. Its location calls for the use of roundabouts to allow the pods to change direction and enter the station. This open space corridor not only serves as a perfect guideway for people to go into the station, but also could become an unofficial entering portal or meeting point for people to later go into the main campus. Our stations are being designed carefully to become more than mere boarding platforms, as they are being given features and spaces that foster socialization. One of the purposes of this station's design is to become a place of reunion and social interaction. That is why we are planning all of our stations with different types of services, such as last-mile vehicle stations, to help people move around, whether they are using the system or not. The South Station. Our southmost station is located at the sports campus next to the Spartan Stadium. Next to the main parking area of the Spartan Stadium, we found a lot big enough to locate this type of station that demands a lot of space. It is the largest of our stations, as it must be able to support a flow of a large number of users during sporting events. Considering the amount of people that would come through this station, this design includes ramps as an additional way to leave the station. Taking advantage of the stadium's parking lot, this station could provide an alternative parking solution to car owners, as they could leave their cars at the stadium and then take the system to get to the main campus, thus helping diminish congestion at the main campus parking buildings. The modularity of our architectural design and quick building method will permit stations to grow or decrease in size according to the space available, as can be shown by our next example, the Central Station. This is our most compact station, designed to be the minimal expression of our concept, so that it can fit anywhere where there is some underused urban space. The central stations are meant to be located between the north and the south stations, near some schools and offices, taking advantage of the space provided by their parking lots. The installation of the station would not interfere with the use of such spaces. This would be the type of station more frequently used, as it is the most economical to build and the most practical and adaptable. After a complicated and time-consuming design stage, we started to look for technologies that would not only make possible all of the proposed functionalities, but that would also transform our stations into special living spaces. Transparent TV screens, light panels, and other technologies that should be affordable in the next 5 to 10 years. One of the most important concepts about our stations that began as a simple idea that evolved over time was the possible involvement of large corporations based in Silicon Valley in the construction, management, and maintenance of the stations. These images are just some examples of how the relationship between the company Adobe and one of our central stations might look like. We chose Adobe as our experimental sponsor company for its colorful brands and logos. The possibilities are truly endless.
A user journey map is usually associated with software design, but in general terms, it is a design tool used to gain insights about all of the different interactions the user has with a product, service, or system. And it is mainly achieved by systematically tracking and analyzing all the steps of the user throughout the entire experience.
To create the user journey map of our system, we developed a persona to provide our design team with a shared understanding of the users in terms of goals and capabilities. User journey. The journey begins when the person interested in using the system is able to program her trip through an easy-to-use app that, among other features to help its usability, will have voice commands for people with special needs. Once a trip is pre-selected, the user can walk or take last-mile vehicles to get to the station. The stations will have regular and electric stairs, as well as an elevator to help cyclists and people with special needs to get to the overhead platform with their personal vehicles. Once at the elevated platform, the user will have to look for the special turnstile so that she can go through it with her bicycle. The app will then send a message telling the user which gate to go to and which space to occupy in the waiting area. The user will use the signs on the floor and walls to look for her assigned gate. An identification pattern will appear both on the app display as well as on the surface of the gate doors for the user to verify that she is in fact waiting in the right place. Once the pod arrives, a message will appear on the gate doors to alert incoming passengers to wait for the egress of outgoing passengers. The user must remain standing on her waiting spot, allowing the egress process to take place without obstructions. The gate doors will close again to permit the sanitization process. This process is optional because the ventilation filters inside the pod take care of keeping the interior clean during the rides. If the user asks for it, a special spray will provide extra sanitization. Finally, the doors open, allowing the user to board the vehicle. Special signs will indicate her assigned seat, and only the required seats will be deployed. The user will find a special rack to secure her bicycle, as she previously requested this feature on her app. Once her bike is secured, the user takes her place. Only after she has secured her seatbelt will the pod close the doors and start the ride. The riding experience will be like none other you have experienced before. Personal, safe, fast, smooth, and very enjoyable. Once the pod has safely attached itself to the station, the doors will open, allowing the passengers to get off, ending the ride. After the user gets off the pod, the whole process begins again. As we have seen before, some of our stations will be enabled with a ramp, which can be used especially when a bike or other vehicles are involved. The overall idea is to provide a service like none other ever devised before. Safe, practical, efficient, and enjoyable. We have shown the vision of how urban transportation can be done with solar energy, what it will look like, and how a user would experience it. There is still much to be done in the next few years to fully realize the vision and implement it around the world. If you can contribute, please contact us to join our project.